imagine, if you will, that you're standing directly beneath, like a massive wind turbine.
Oh, those are incredible up close. The sheer scale is just wild.
Right. You look up and there are these enormous sweeping blades just carving through the air. And they're driving a gearbox up there that costs more than a very nice house.
Yeah, easily. Millions of dollars of engineering just suspended in the sky.
Exactly. Or, picture yourself looking out over a sprawling tank farm at a petrochemical plant. We are talking about millions and millions of dollars of heavy industrial machinery.
Which is a massive investment to protect.
It is. But now, what if the biggest threat to these mechanical titans isn't a hurricane, or an earthquake, or some kind of catastrophic structural failure?
Right, the things you'd normally expect.
Yeah, what if the thing most likely to bring them grinding to a halt is just microscopic dirt, or just simple, everyday moisture in the air?
It's totally counterintuitive, but that is the reality.
So how do these colossal machines actually survive that kind of invisible assault?
Well, it's an entirely counterintuitive problem, like you said. When we look at the sheer scale of, say, a mining operation or a pulp and paper mill, we naturally assume the protective measures must be equally massive.
Right, like thick steel armor, giant cooling towers, that sort of thing.
Exactly. But the reality is that the most critical battles for a machine's lifespan are actually fought at the microscopic level.
Oh, wow.
Yeah, you have to protect the internal fluids from the ambient environment, or the equipment simply tears itself apart from the inside out.
And that invisible battleground is exactly why we're here today. So welcome to your custom-tailored deep dive.
Glad to be here for this one. It's a fascinating topic.
Today, we have a single, highly technical source in front of us. It's the official specification sheet for a device called the Desiccant Extended Series Breather.
And on the surface, it's a dense list of engineering tolerances, materials, flow rates. It looks pretty dry.
Yeah, super dry. But our mission today is to decode this tech sheet, because hidden inside these numbers is this brilliant story of mechanical problem solving.
It really reveals exactly how the world's heavy industries keep their lifeblood, their oils and lubricants pure.
Okay, let's unpack this, because to understand how these breathers protect a wind farm, we first have to understand what this device actually is at an anatomical level.
That is the perfect place to start. If you consider an industrial storage tank or a massive gearbox, it's rarely a sealed, static system.
Right, things are moving.
Yeah, fluid is constantly being pumped in and out, and internal temperatures are constantly fluctuating.
It's dynamic.
Highly dynamic. When fluid leaves the tank, or when the internal temperature drops and the air inside contracts, the machine has to draw in ambient air from the outside just to equalize the pressure.
Basically, the machine has to breathe.
Exactly. It takes a breath.
And if it's breathing in the air of, like, a dusty mining site or a super humid paper mill, it's inhaling rock dust and water vapor straight into its hydraulic fluid.
Which is a death sentence for those internal components.
So these decase breathers act as this heavy-duty, multi-layered respiratory mask for the machine.
That's a great way to look at it.
And looking at the spec sheet for the materials they use to build this mask, it reads like a recipe for surviving a war zone.
Oh, absolutely. They do not mess around with the housing.
Right. We've got a housing made of nylon 66 that is 30% glass filled. We have polycarbonate, polypropylene, silicone, and it's all sealed up with EPDM seals.
It's quite the cocktail.
It is. But I want to understand the why behind this specific cocktail of plastics and rubbers. Why not just build it out of steel or, standard PVC?
Well, every single material choice there is solving a specific environmental hazard. Let's take the nylon 66, that's 30% glass filled.
Okay, yeah. Why the glass?
Because standard plastics become really brittle under constant vibration. By infusing the nylon with microscopic glass fibers, you dramatically increase its structural integrity and its fatigue resistance.
Oh, which makes sense if you're bolting this thing onto a heavy vibration source like a wind turbine gearbox.
Precisely. You need it to survive the shaking. Then you have the polycarbonate housing. Polycarbonate gives you the absolute clarity of glass, which is necessary for a visual inspection, but it has incredibly high impact resistance.
So if a technician drops a wrench on it, it won't just shatter into 1,000 pieces and contaminate the whole area.
Exactly. It's tough as nails, but totally transparent.
That makes the EPDM seals make a lot more sense, too. Because standard natural rubber degrades and swells when it gets exposed to synthetic oils or extreme UV light, right?
Yeah, it breaks down fast. But EPDM is an artificial elastomer, specifically formulated to resist that exact kind of chemical degradation.
So the housing itself is virtually indestructible, But the actual filtration is where I really want to push back on the source a bit.
Oh, what caught your eye?
Well, the spec sheet states the filter efficiency is 3 mmM absolute, so 3 microns.
Right. 3 microns absolute.
On paper, creating a 3-micron physical barrier sounds super impressive. But in the real world, say, in a coal mine, wouldn't a filter that fine just act as a cork?
You'd think so, yeah.
I mean, wouldn't it clog up instantly with ambient dust and completely suffocate the machine? Why isn't a 3-micron brick wall actually a massive liability?
That is the core challenge of filtration engineering, actually. You're constantly balancing capture efficiency with flow capacity.
Okay, so how do they avoid suffocating the machine?
The reason it works is due to the surface area of the pleated filter material inside the housing. They maximize the square footage of that filter media so the air has plenty of pathways.
So even as parts of it get dirty, there's still room for air to get through.
Exactly. And the reason they insist on that specific 3-micron threshold, and really emphasize the word absolute, comes down to the mechanical clearances inside the machinery it protects.
Because if a particle is small enough to slip past the filter, it ends up directly in the oil.
Precisely. And in high-performance hydraulic systems or heavy-duty gearboxes, the clearance between two moving metal parts is often in the range of like 5 to 10 microns.
Wow, that is incredibly tight.
It is. So if you use a standard nominal filter that lets a 5-micron particle through, that particle is the exact perfect size to wedge itself into the microscopic gap between those gears.
Oh man, so it acts like a tiny microscopic cutting tool.
Yes. It scores the metal, which generates more metal shavings, and that initiates a catastrophic chain reaction of wear.
That's terrifying.
Oh.
But by establishing a 3-micron absolute barrier, you guarantee that any particle entering the system is too small to bridge that gap.
Exactly. It simply flows through, suspended in the oil, without causing any abrasive damage at all.
So it's a totally non-negotiable threshold for preserving the metal. Okay, so we've stopped the dirt, but we also mentioned moisture earlier.
Yes, moisture is just as destructive.
Which brings us to the visual cue that I find so fascinating in this tech sheet. Inside this rugged polycarbonate housing is the hydrophilic media, which this source identifies as silica gel.
Yeah, the classic silica gel.
Right, we all know silica gel. It's the stuff in those little packets you find when you buy a new pair of shoes. But here, they're deploying it on a massive industrial scale.
What's fascinating here is how the source highlights a feature called the color indication.
Oh, right, the color changing aspect.
Yeah. As the silica gel chemically bonds with the water molecules from the incoming air, it undergoes a really distinct color change from blue to pink.
Which solves a massive logistical nightmare for maintenance crews, I'd imagine.
Oh, you have no idea.
I mean, if you have a technician inspecting a tank farm with dozens of these breathers, or someone climbing hundreds of feet up a wind turbine, they don't want to mess with fragile sensors.
No, they don't need to hook up a diagnostic laptop or rely on digital humidity monitors just to know if the breather is saturated.
The chemical color change provides a flawless, immediate visual cue. If it's pink, the desiccant is full. It just completely removes the guesswork.
It really does. It's elegantly simple.
But thinking about this mechanically, I see a glaring vulnerability here.
Okay, let's hear it.
If the polycarbonate is perfectly clear, and we have a tube full of silica gel sitting on top of a machine in the middle of, say, a humid Louisiana summer,
Oh, yeah.
won't it just constantly absorb moisture from the ambient atmosphere? If it's just an open pipe into the machine, it seems like the desiccant would turn pink and be ruined in a matter of days.
Just pulling humidity right out of the breeze.
Exactly. It seems like a huge waste.
Well, you've identified the exact engineering hurdle that defeats standard open breathing systems.
Okay, so I'm not crazy.
Not at all. If the desiccant bed is permanently exposed to the ambient atmosphere, it will continuously pull moisture from the environment until it's entirely saturated.
It ends up wasting its chemical capacity, drying out the outside world, rather than protecting the machine's internal environment.
Exactly.
Well, here's where it gets really interesting, because this vulnerability leads directly into what might be the smartest feature of the entire device.
The check valves.
The check valve technology, yes. The spec sheet specifically lists a metric called check valve cracking pressure, and the number they list is tiny. It's 0.1 psi or 0.007 bar.
That 0.1 psi figure is the linchpin of the entire extended series design.
I was trying to visualize what a 0.1 psi cracking pressure actually means in practice. And it seems like it functions very much like a highly sensitive bouncer at a very exclusive nightclub.
Okay, I like this analogy. Run with it.
So most of the time, the bouncer stands there with the doors completely sealed shut. The club, which in this case is the silica gel bed, is totally isolated from the outside street.
Right.
It doesn't matter how humid it is outside. The doors are locked.
Let's apply that bouncer analogy directly to the fluid dynamics of a massive storage tank to see why that precise sensitivity is so vital.
Okay.
The crowd trying to get into your nightclub is the atmospheric pressure, but the bouncer only responds to the vacuum pressure created from inside the building.
Oh, that makes sense.
So imagine a 1,000-gallon storage tank full of hydraulic fluid. A massive industrial pump kicks on and rapidly removes 100 gallons of that fluid to actuate a piece of machinery.
That sudden void inside the closed tank creates a vacuum. The internal pressure drops rapidly because something has to fill that empty space.
The moment that internal pressure drops by exactly 0.1 psi relative to the outside atmosphere, the vacuum physically pulls on the check valve mechanism.
So the bouncer feels the pull from inside and unseats the valve.
Exactly. This allows the machine to safely inhale. The atmospheric air rushes past the valve through the 3-micron pleated filter to strip the dirt.
Catching all the dust.
Right, and then forces its way through the tortuous path of the silica gel bed. The silica strips the water molecules out of the air, and perfectly clean, perfectly dry air enters the tank to replace the missing fluid.
And then the moment the pump stops, the pressure inside the tank equalizes with the outside air. The vacuum disappears.
And the bouncer shuts the door. The spring-loaded check valve seats itself again, completely sealing off the desiccant from the ambient environment during all periods of inactivity.
So the breather only works when the machine demands it.
Yeah. That isolation is precisely why they're called the extended series. These check valves extend the active life of the desiccant exponentially compared to an open system.
It is an incredibly elegant solution. But since these breathers are being deployed on everything from standard hydraulic reservoirs on a factory floor to massive outdoor tank farms, a one-size-fits-all approach physically cannot work.
No, the engineering has to scale.
And that brings us to the sizing matrix in the tech sheet, which outlines 4 distinct models: the DCEX1, the DCEX2, the DCEX3, and the largest, the DCEX4.
The physical differences between the EX1 and the EX4 give us a great window into how dramatically the fluid volume demands vary across different industrial applications.
Looking at the extremes here paints a pretty clear picture. The smallest unit, the DCEX1, is 4.7 inches high.
Pretty
Right. It holds 1.2 pounds of desiccant and has a maximum water retention capacity of 7.7 fluid ounces.
Which is roughly half a bottle of drinking water.
Exactly. Now compare that to the massive DCEX4. This unit stands 10 inches tall. It holds 4.2 pounds of desiccant, and it traps an impressive 27 fluid ounces of water.
Yeah, that is well over 1.5 pints of water that it's actively sequestering away from your machinery.
Which is a monumental amount of protection, right?
Oh, absolutely. When you consider the chemistry of industrial lubricants, even a single teaspoon of water, when emulsified into high-performance hydraulic oil under extreme pressure, can completely destroy the oil's viscosity.
Just a teaspoon.
Just a teaspoon can lead to total system failure.
Wow. But as I was reading through the source's data table, looking at how the specs change across these 4 models, I found a metric that seems to contradict the very idea of scaling up.
You notice the airflow numbers.
I did. As the units get bigger, from the EX1 up to the EX4, the amount of desiccant goes up, the overall height goes up, the total water capacity goes up.
Naturally.
But the source indicates that the maximum airflow at a 1 psi pressure drop actually decreases slightly as the unit gets bigger.
Ah, yes, the airflow paradox of the extended series.
Exactly. The tiny EX1 allows 27 cubic feet per minute of airflow. But the giant EX4, the biggest, heaviest breather in the lineup, only allows 24.
It seems wrong, doesn't it?
It really does. Why would adding size and capacity reduce the maximum airflow? If I have a bigger breather, should it be able to handle a bigger, faster breath?
It's a brilliant observation, and it perfectly illustrates the physical trade-offs in mechanical engineering.
Okay, so what's the limiting factor?
To understand the drop in cubic feet per minute, you have to look closely at the dimensions section of the source material. You'll find a crucial bottleneck, the thread size.
The thread size.
Yeah. All 4 models, from the tiny EX1 to the massive EX4, mount to the machinery using the exact same connection, 0.1-inch female FNPT thread.
Oh, okay. So the actual doorway into the machine, the pipe connection, is the exact same diameter for all of them.
That is the bottleneck right there.
Mm-hmm.
Now, combine that static doorway with the physical reality of the desiccant bed.
Right. There's way more silica in the big one.
Exactly. The larger models, like the EX4, contain a much thicker, heavier bed of silica gel. You're jumping from 1.2 pounds of densely packed granular beads up to 4.2 pounds.
I see. So even though the exterior housing is much larger, the incoming air has to fight its way through nearly 4 times as much physical material before it can reach that same 1-inch doorway at the bottom.
Exactly. Pushing atmospheric air through a vastly thicker bed of granular desiccant naturally creates more physical resistance.
That makes totally sense.
Therefore, at the exact same pressure drop of 1 CI, the flow rate is going to be slightly restricted by that extra material. That's why you see the maximum cubic feet per minute drop from 27 on the EX1 down to 24 on the EX4.
And consequently, you see the exact same proportional drop in the maximum fluid displacement rating.
Right.
The EX1 can handle a system pumping 202 gallons per minute, while the EX4 is rated slightly lower, capping out at a 180 gallon per minute displacement.
That is perfectly linear with the airflow restriction.
That makes perfect mechanical sense when you visualize the tortuous path the air has to take through the beads.
It really does.
Understanding those specific airflow limitations means engineers can't just blindly slap the biggest breather onto every machine and call it a day.
No, definitely not.
They have to consider exactly where and how these different models will be deployed in the real world. Which brings us to the environmental limits and the sizing guidelines.
These are crucial to get right.
First, the environmental extremes this housing can survive are staggering. The tech sheet states the operating temperature range is from negative 20 degrees Fahrenheit all the way up to 200 degrees Fahrenheit.
If we connect this to the bigger picture for our international listeners, that is negative 29 Celsius up to 93 Celsius.
That's boiling point almost.
Basically, yeah. The device is built to operate flawlessly, whether it's bolted to a freezing mining rig in the dead of a Canadian winter or baking on a manufacturing floor inches away from heavy heat-generating equipment.
It also boasts chemical compatibility with all mineral oils, most synthetic oils, and diesel fuels. It really is an armored tank of a filter.
It has to be.
But when it comes to actually choosing which of the 4 models to use, the sizing chart reveals some fascinating discrepancies.
Oh yeah, the application matters immensely.
If we look at the sizing recommendations for a gearbox or a storage tank versus a hydraulic or a central lube reservoir, the numbers change drastically.
They do.
If you have a standard gearbox or a storage tank, the big DCEX4 can handle a massive 1,000-gallon system. But if you have a hydraulic or central lube reservoir, that exact same DCEX4 is only rated to protect a 400-gallon tank.
A huge difference.
That is less than half the fluid volume.
Okay.
Why does the application change the rating so severely?
Well, it comes down to the behavior of the fluid, specifically the frequency and velocity of the fluid movement.
Okay.
A 1,000-gallon bulk storage tank might sit idle for days or weeks. It only takes slow, massive breaths when a delivery truck eventually arrives to drain or fill it. The check valves remain closed 99% of the time.
So it's barely breathing.
Exactly. But a 400-gallon hydraulic reservoir is an incredibly active, violent system. Fluid is rapidly and continuously circulating to actuate heavy cylinders and drive motors.
Oh, I see.
The breather on a hydraulic system is working relentlessly, inhaling and exhaling constantly as the fluid levels surge and dip every few seconds.
Which means the desiccant is going to saturate exponentially faster, even though the total volume of the tank is much smaller. The bouncer's constantly opening the door.
Precisely, which is why the source material includes a highly critical caveat note 2 in the application sizing recommendations.
Right.
The engineers at Desiccant explicitly warn that sizing a breather is not a simple linear math problem based solely on tank volume.
Yeah, Note 2 says that sizing is just a general guideline, and that several other variables are absolutely vital to calculate.
They list those variables clearly: humidity level, frequency of airflow, ambient temperatures, and chemical compatibility.
So it's very context dependent.
Highly. Consider 2 identical 1,000-gallon storage tanks. If you install an EX4 on a tank sitting in a climate-controlled, relatively dry data center as part of a backup generator system, that breather might last well over a year.
Because it's a cushy environment.
Right. But if you put that exact same EX4 on a 1,000-gallon tank in a sweltering, unair-conditioned paper mill in the deep south with 100% ambient humidity, and the tank is cycling its fluid every 20 minutes.
Oh, man.
Yeah, the desiccant will turn pink and max out its 27-ounce water capacity in a fraction of the time.
So you really have to view it as an entire localized ecosystem, not just a standalone part.
Right.
You have to understand the specific atmospheric challenges of the room it sits in.
Special circumstances require thorough analysis. The ultimate takeaway from the sizing matrix is that even the absolute best 3-micron filter, backed by precision check valves and over 4 pounds of chemical silica gel, is entirely useless if it's applied blindly.
Right. If you placed it in an environment that overwhelms its flow rate or its moisture capacity, you lose the protection entirely.
The brilliant engineering only works if it's applied with an understanding of the physics involved.
So what does this all mean? We started this deep dive by looking at a massive wind turbine and a multi-million-dollar petrochemical tank farm.
And we asked how they survive.
Right, how these mechanical titans survive the invisible, relentless threats of microscopic dirt and atmospheric moisture. And the answer, as we've decoded from this single, dense technical spec sheet, is a masterpiece of passive engineering, the extended series breather.
It truly is a remarkable piece of functional industrial design.
Think about what this single device achieves without a single battery, wire, or microchip.
It's entirely analog.
Yeah. It survives 200-degree heat and heavy vibration. The largest model chemically traps over 1.5 pints of water before it reaches capacity.
It's doing so much heavy lifting.
It acts as an absolute brick wall against 3-micron invaders, catching particles that are a fraction of the size of the clearances inside the gears.
All while perfectly managing its own lifespan.
Exactly, by utilizing physical pressure. Opening its check valves only when the internal vacuum drops by exactly 0.1 CI, keeping the desiccant locked away until the machine actually needs to breathe.
Which is brilliant.
And when the silica finally reaches its chemical limit, it requires no digital diagnostics. It simply turns from blue to pink to let the technician know its watch has ended.
It communicates and protects purely through applied chemistry and fluid dynamics.
It really is something you will never unsee once you know how it works.
Yeah.
So the next time you are driving past a wind farm and you see those massive turbines spinning against the sky.
Or you catch a glimpse of heavy manufacturing equipment in a factory.
Exactly. I want you to look a little closer at the machinery. Look for these brightly colored silent sentinels. These rugged blue or pink cylinders bolted to the steel. They are standing guard over the machine's lifeblood, fighting an invisible war so the heavy lifting can continue.
This raises an important question, especially for you as you consider how we build and protect critical infrastructure today.
How so?
Well, we've spent this deep dive exploring how a multi-million-dollar physical asset can be perfectly safeguarded by relying entirely on the unchanging laws of physics. A mechanical spring unseating at 0.1 CI, a physical 3-micron barrier, a chemical color change.
Right, it's elegant.
And it is infinitely reliable because it cannot suffer a software glitch or a power outage.
Oh, wow, yeah. That's a great point.
Yet, when we look at the modern electrical grids, the data centers, and the interconnected systems we're building today, we are increasingly stripping away physical fail-safes in favor of incredibly complex, fragile digital monitoring.
Everything has an app or a sensor now.
Exactly. It makes you wonder, what are the hidden vulnerabilities in our modern hyper-connected infrastructure that might be far better protected if we stopped relying on software and returned to the brilliant, infallible reliability of passive analog design?